Welcome to The Explainer. Today we're going to crack open a secret toolkit from mathematics, one that lets you solve problems that seem, well, completely impossible.
So, to get us started, check out this quote from our source. It really gets to the heart of what we're talking about today, the art of finding these incredible shortcuts to certainty.
So what does counting without counting actually look like in practice? Well, think about this classic puzzle. You've got 100 prisoners. They're facing a life-or-death logic game. And here's the kicker. They can't talk to each other, but they have to get it right. As we're about to see, all they really need is the right way to think.
Now, the solution here isn't some cheap trick. It's actually a set of really powerful thinking tools. These are elegant principles that let us find absolute certainty even when things look incredibly complex. So let's open up that toolkit and have a look at our first tool.
Okay, this first principle, it sounds so simple, almost obvious, but trust me, the implications are huge, and it's actually the foundation for everything else we're going to talk about.
This isn't about chance or probability. It is a 100% mathematical guarantee. Think about it. If you have, say, 11 letters to deliver, but only 10 mailboxes, one of those mailboxes has to get more than one letter. It's just unavoidable. And that certainty is where its real power lies.
All right, so let's apply this idea. Let's take a simple problem. In this case, just think of the people as our pigeons, and the months of the year, well, those are our pigeonholes.
So, you've got 13 people, our pigeons, but only 12 months in a year, our pigeonholes. It means a shared birthday month isn't just likely, it's a mathematical certainty. And get this, we don't need to ask a single person for their birthday to know this. The principle just guarantees it. See, that's the magic of counting without counting. All right, let's grab our next tool. We're about to see how this simple idea builds into something truly mind-bending. This is a principle that basically proves complete and total randomness is impossible. In any system that's big enough, little pockets of order are guaranteed to show up. This leads us to the famous problem of 6 people. Now, it seems like you should be able to arrange the relationships to avoid this outcome, right? But the math says, nope, you actually can't. There's a hidden structure that's always there. Okay, so to get our heads around this, let's try to visualize it. Imagine the 6 people are just points, and we'll draw a line between any 2 of them to show their relationship. Let's say if they're friends, the line is blue. If they're strangers, it's red. And would you look at that? Our first tool is back in action. So, pick one person, P0. He has 5 connections to the other people. Those 5 connections are our pigeons, and they can only have 2 types, friend or stranger. Those are our pigeonholes. So that means P0 must have at least 3 friends or at least 3 strangers. It's guaranteed. And this is where it gets really clever. So we know for a fact that P0 is friends with at least 3 other people. Now all we have to do is look at the relationships between those 3 people, and that's going to give us our answer.
Okay, this is the final step, and it's brilliant. Just look at those 3 people. Case 1, if any 2 of them are friends, boom, they form a blue triangle of friends with P0, and we're done. But what if none of them are friends? Well, that means they must all be strangers to each other, forming a red triangle of strangers. Either way, you're forced to make a triangle. The search is over.
So it doesn't matter how you try to arrange the friendships. A pocket of order, that triangle of friends or strangers, is mathematically guaranteed to pop up. It's an incredible idea, really. Complete and utter chaos is impossible.
All right, our final tool is one of the most elegant concepts in all of mathematics. It's a way to prove if something is possible or impossible just by finding a property that never, ever changes.
Think of it like this. No matter how you rearrange the furniture in a room, the total number of chairs stays the same. The number of chairs is an invariant. Or with a Rubik's Cube, however you twist it, the center pieces never change their positions relative to each other. Once you find the invariant in a problem, you've found the system's one unbreakable rule.
At first glance, this seems doable, right? I mean, you can just keep adding ones and eventually they should all even out. But an invariant is going to tell us the truth, and it might not be what you think. So, to find this system's secret fingerprint, we're going to define something called the alternating sum of the numbers. It's simple. You take the first number, subtract the second, add the third, subtract the fourth, and so on. In our starting position, that sum is 2. But in our target, where all the numbers are the same, that sum would have to be 0. Now here's the key insight.
The only move we can make is adding 1 to 2 numbers right next to each other. So what does that do to our alternating sum? Well, if we add 1 to 2 neighbors, one gets a +1 and the other gets a -1, which adds up to 0. Our move has no effect on the sum. The sum is constant, it's an invariant.
And there it is, that's our answer. This proves with absolute certainty that it doesn't matter how many moves you make, you can never reach the goal. The system's fingerprint is 2, and it can never become 0. The task is impossible. Case closed.
So let's zoom out for a second. What have we learned from opening up this mathematical toolkit? What's the big picture here?
We've just walked through 3 incredibly powerful tools that let us understand these complex systems without having to check every single possibility. We've seen how you can guarantee a shared birth month, prove that social structures are literally inevitable, and even show that some puzzles just can't be solved.
But really, the big takeaway here isn't about pigeons or prisoners. It's about a whole new way of seeing the world. Combinatorics gives us this amazing lens to spot the hidden patterns and the unbreakable rules that are all around us, in everything from social networks to the very fabric of possibility itself.
And that's something to chew on until our next explainer.